Hello, everybody. My name is Said Al-Kazmi de Pedraza, and I am the doctoral candidate number 9 of the Marie Curie project in NOVA. In this part of the presentation, I will introduce you what are the transfer paths of noise and also how to account for them. So, where does that noise come from? Imagine that we have a noise source given by this loudspeaker, for example, and a receiver, which would be, for example, a house, car, an aircraft, whatever. So what are the main paths between the noise source and the receiver? Well, first, an airborne path that is directly the noise that you receive from the source. And secondly, the structure-borne path, which is the path that accounts for the transfer of vibration through solids. So, is it really rocket science? Well, actually, not. What is noise? Noise is the consequence of the vibration of solid things and other stuff that sounds or other sound sources. Consider, for example, a guitar. What happens with the guitar? When we play the guitar, first of all, we play the strings. The strings vibrate. The vibration of these strings, they transfer into the guitar. And there are three paths that go to the guitar. First, an structure-borne path, which is divided in two subpaths. So first, the vibration transmits to the body through the bridge and the headstock. So the bridge is this part here in which the strings are inserted to the guitar. And this is the headstock, where the strings are tuned to have the perfect pitch for the guitar. Then an airborne path, which is constituted by the vibration, well, by the sound waves that the strings create, and they enter directly the sound hole. So the strings vibrate and they go inside the body of the guitar through the sound hole. But we are not only interested in what happens inside the guitar. Moreover, we are interested on what happens outside. What do we hear? So there are two main paths out of the guitar, namely an airborne path. So the sound resonates in the resonance box and exits the sound hole. So it actually goes outside from here, but also on a structure-borne path, because the wood of the body vibrates and creates sound waves that reach the listener. So for example, these parts here of the guitar, they vibrate and they generate some sound that we finally receive as a listener. Now the question is, why should we know? As this famous quote by Peter Drucker, if you can measure it, you can improve it. It happens the same with acoustics. So imagine that you want to improve the sound of your products, or you want to reduce the sound in enclosed spaces such as houses, cars, aircraft, trains, or you want to design a noise reduction strategy using, for example, active noise control or passive noise mitigation, and many more. What you need is to quantify and rank the transfer paths of noise. Very simple. Now the question is, what's next? Well, I will introduce you my PhD topic, the contribution analysis of vibrating aircraft interior parts to overall cabin noise. So imagine that you are inside an aircraft, you're seated on your seat, waiting for the takeoff, and then you start listening to the sound of the engine, the sound of the things that you don't know actually. The problem is, how can we reduce the sound without actually, we can if we don't know where this sound comes from. So there are many sources inside the cabin that account for this source, namely the ceiling panels or the sideway panels, or even the floor. All these panels, they vibrate and they generate sound inside. But actually this sound is not generated inside the cabin. It comes from the vibration or the sound outside the aircraft. It can also be generated, for example, from the engines or from the vibration of the rotor of the engines that transmits into the structure of the aircraft, or the air because of the high speeds, so on. The question is, what is the starting point of all of this? So what are the questions that we want to resolve with this PhD? So the first question is, where does the noise inside the cabin's aircraft come from? The question 2 is, how can we account for this transfer path of noise? And the third question is, can we use simulation for this? The current state of my PhD is that there are methods to account for the transfer paths using simulation, but these are still in development and haven't been yet applied to the real case of an aircraft. But the prospection of my PhD is that by the end of my study, these methods will be applied to a simulation model of a real aircraft, and the transfer paths and the contribution of interior parts will be accounted. And well, this is all related to transfer path of noise. And now Sulfi, the doctoral candidate number 3, will introduce you the topic of noise barriers. Thank you very much.